Alright, guys, welcome to the MATH1231 and 1241 workshop. So today is our first half of the workshop, in which we will be going through the topics in calculus. So this is presented by the UNSW Maths Society, and here we have a list of the topics that we will be going through today. So essentially, for the first half of today's lecture, so the first hour, we will be having a look at the first three topics. And then we will have a short break, after which we will then get another presenter named Wendy, who will be going through with you the last two topics, which are Taylor series, as well as the applications of integration. All right, so let's get started. So our first topic over here is our functions of several variables. And the very first concept that we will be covering today is the idea of partial differentiation. So this topic is comparatively easier than the others. So just to get us started, let's have a look at the idea of partial differentiation. All right, so when we are dealing with functions with several variables, for example, this function f over here, which is equal to x squared plus xy plus y squared. So for these types of functions, which involve several variables, if we want to find the rate of change with respect to either variable x or y, then we must apply the technique of partial differentiation. And applying the technique essentially just involves treating all variables other than the one we're differentiating with as constants. Or just also additionally, these slides will be published on the Math Society website in case you need to refer to them later. Yeah. Right, so here's an example of how we can apply partial differentiation. So if we have this function f, and we want to take the partial derivative of f with respect to x, then what we can do is we can keep all the y's, which are not the constant, the variables that we are differentiating with respect to. And then what we're left with is 2x plus y. Yeah, because we're taking all these y's as constants. Now, alternatively, if you want to take the partial derivative of f with respect to y, then you can take all the x's as constants, and you're going to end up with x plus 2y instead. Yeah, so that should be all right. Moving on, we have an application of the idea of, or technique of partial differentiation, which is essentially just tangent planes to surfaces. So essentially, if we've been given a function of the form f, x, y, z, so as you can see, this is the function in terms of three variables is equal to 0, then the normal vector at the point P given by x0, y0, and z0 on f is given by this particular vector over here. And if you don't remember this notation where we use the subscript, so f subscript x essentially just denotes the partial derivative of f with respect to x. And similarly, this would be the partial derivative of f with respect to y. And importantly, this has to be evaluated at P. And we'll have a look at what that means a bit later when we go through an example question. So once we get this normal vector of the plane, what we can do is then using the point normal representation of a plane, which, if you remember, is what we covered in Math 1131 and 1141, to actually find the equation of the tangent plane. And how we can do that is the dot product between the normal vector and x, which is a point on the plane, x, which is essentially the vector x, y, z, take away by p, which is a point on the plane, given by x0, y0, and z0 in this particular scenario. Right. So now let's have a look at a past exam question taken from 2014. So the question just says, show that the tangent plane to the paraboloid S given by this particular expression over here at the point P is equal to x0, y0, z0 is given by this expression over here. All right, so what's the first thing we do, right? So if we scroll back to the previous slides, it tells us the first thing we want to do is to actually find the normal vector of to the tangent plane. And how we can do that is to actually rearrange our expression here into the form f x, y, z is equal to 0, and then we can take the partial derivatives of f with respect to x, y, and z. Let's have a look at how we can do that. So if we rewrite it in the form that we want, we end up with just moving everything to the left-hand side. Yeah. So then what we can do is that we can take the partial derivative of our function f over here. And that involves treating all other constants as, all other variables as constants. What we're going to get would be this. Yeah? So now that we have the partial derivatives that we require to actually find the normal vector, we can then substitute that into a point normal representation of a plane. Yeah? So that's exactly what we've done over here. So this is our normal vector that we just evaluated. And then we put it into this particular formula that we had, and then let it be equal to 0. Yeah? Now expanding the left-hand side of our equation over here using the definition of dot product, this is what we end up with. Now, all that left is to actually rearrange using some algebra to get to this expression that we want to get. Yeah, and what we did over here is to actually move all these expressions to the right-hand side. And that's how we get to the second line. And then we divide everything by 2, and then eventually, as you can see, we end up with the exact expression that the question is asking for. Right. So moving on. The second application of partial differentiation that we will be covering is the idea of total differential approximation, and it's given by this formula over here. And if you don't remember, basically the rationale behind this expression is essentially saying that because we're dealing with this function f over here, which is dependent on 2 variables, both x and y, then if we want to find a change in f, then obviously that will both depend on changing x and changing y. And exactly how they relate it is through the partial derivative over here. So remember, partial f, partial x essentially just means the rates of change of f with respect to x. So it makes sense that the rate of change of f, the change in f would just be equal to the change in x times the rate of change of f with respect to x plus change in y times the rate of change of f with respect to y. That probably sounds like a mouthful, but if you think about it, there is some intuition behind it. Alternatively, if you want a more rigorous and more in detail explanation of how we got to this total differential approximation formula, you can refer back to the course notes. Yeah, but it just comes from the equation of a tangent plane as well. Right, so let's have a look at another question where we can apply the concept of total differential approximation. So this question comes from a 2012 exam. Essentially, the area A of an ellipse have the form of this expression over here. And if the ellipse is deformed in such a way that A is increased by 4% and B is decreased by 1%, remember the reason why we use percentages over here, you should be thinking about these are relative changes, not absolute changes. And we'll have a look at what we mean by that. Now, use the total differential approximation to show that the approximate relative change of area, which is essentially delta A on A, is independent of both A and B, and hence calculate its value. So this question is actually tells you to apply the concept of total differential approximation. So it makes sense for us to actually try to apply this formula to this question straight away. So in this scenario, we're interested in the change in area. Yeah, and we know because a is a function of variables a and b, then what we can do is to take the partial derivative of area with respect to a multiplied by the change in a plus the partial derivative of the area with respect to b multiplied by the change in b. So this is the expression that we should be starting with. Yeah. And then taking the partial derivative in this case would be quite simple because everything over here is just a constant. So if we want to take the partial derivative of area with respect to a, then it's just b multiplied by this constant. And on the other hand, if it's partial a, partial b, then essentially just a multiplied by this constant, as we will see on the next slide. Yeah. So partial derivative of area with respect to a is just equal to this. And partial a, partial b will just be equal to this expression over here. Yeah. All right. So now if we go back to the question to have a further look at what exactly they want, they actually do not want the absolute change in area. We're only interested in that relative change in area, which is given by delta A on A. Yeah. But on the other hand, if we have a look at our equation, this is our equation for the absolute changing area. And so how we can get from delta A to delta A on A is obviously divide both the left-hand side and the right-hand side by the formula for area, which is AB, and then multiplied by a constant. Yeah. And if you have a look at what's going to happen when we divide both of these terms by KAB, as you can see, the constant K will actually cancel out. The B will actually cancel out. And what we're left with is essentially just delta A divided by A. And the same thing happens over here. Yeah, the constant cancel out and then the A cancel out. So we're left with delta B divided by B. And what does that mean? So when we have an absolute change divided by this particular variable, then we get the relative change. And if you have a look, or if you think back to what we talked about at the start of the question, when we were first going through the information that we've been provided with, we said that there's 4% over here and that 1% decrease are indeed the relative change in variables that we are interested in and what's being required to actually solve the question. So A is increased by 4%. So our delta A on A over here is actually just 4%. Whereas on the other hand, delta B on B, which is the relative change in B, is essentially decreased by 1%, so negative 1%. So that's how we actually get that 4% minus 1%, which gives us a final answer of 3%. Yep. And as you can see, this is indeed, as the question suggests, independent of both the actual values of A and B, because we're only interested in the relative change, not what A and B are actually are. Yep. All right, moving on to error estimation, which is extremely similar to the idea of total differential approximation that we just covered. The only difference is that we are essentially adding absolute value signs on both sides, and then we're using the triangle inequality to actually rewrite this expression so that it's smaller than or equal to this particular expression over here. And the reason why this is useful and will sometimes come up in questions is because this will actually imply that we can use this absolute value of change in f to represent the absolute error of a particular function, in this case the function f. So essentially what we're saying is that the absolute error of this function f has to be smaller than this particular expression here. And as you can see, this expression is written in terms of the absolute error in the variable x, as well as the absolute error in the variable y. Yeah, so that's how we can actually use the idea or the modified idea of total differential approximation in error estimation. Right, so now on to the last concept that we will be covering for the first topic. We have chain rules. Yep, so chain rules essentially, we are again starting off with our formula for total differential approximation. So if you can see, essentially what we've done to our previous formula, delta f is equal to partial f partial x delta x plus partial f partial y delta y. Essentially what we did to this initial equation that we started off with is to divide both sides by delta t. And then using the definition of derivatives, essentially as our delta t over here approaches 0, then our delta f delta t becomes df dt. So it becomes, we can rewrite it in terms of differentiation. Yeah, and so this is the final equation that we end up with, which is quite useful when it comes to solving functions of several variables. So the chain rule can actually be written in a few ways, but then a useful tool that we usually use to actually visualize how chain rule works is through the use of a chain rule diagram, as shown below over here. So as you can see over here, our function capital F here is in terms of two variables x and y. Yeah. So when we want to get to here, we need to apply partial differentiation, so partial f on partial x, as well as partial f on partial y. But then on the other hand, our functions x and y are both functions of a single variable t. So if we want to get to, if we want to get from x to t, then we can just apply normal differentiation dx dt as well as dy dt. So this is probably the most simple scenario that we're dealing with. So on the next slide, we'll be having a look at a more complex scenario where our functions x and y are now also a function of multiple variable. So as you can see, x is defined in terms of s and t, and y is also defined in terms of s and t. So that becomes a little bit more complex, but again, with the help of our chain rule diagram, we can visualize the path, that we can take. Yes, if we want to get to partial f on partial s, essentially we are considering the two different routes that I can take. So partial f partial x multiplied by partial x partial s, which is our first term over here. And then our second term would just be partial f on partial y multiplied by partial y on partial s. So the very similar thing happens if we want to take the partial derivative of f with respect to t, where we will be considering these two routes instead. Yeah. Right. Now onto our third type of chain rule, or a third form of chain rule. Essentially, it's just where our function f is only in terms of a single variable u, and then our u is a function of two variables x and y. Yeah. So again, by using a chain rule diagram, it becomes a lot more easier for us to visualize how we can actually get to both partial f partial x as well as partial f partial y. Yeah. Moving on, essentially this is the exact same concept. It's just slightly more complicated, I guess. So there are more routes for you to consider. So as you can see, just to show you, yeah, what we end up with is seems quite scary, but it becomes really easy if you just consider all the different paths that you can take. All right, so that was the end of our first topic. Now on to the second topic, which is our integration techniques. So the first type of integrals that we will be looking at are essentially trigonometric integrals. Yeah. And then we will be having a look at the integrals which are in the form of sine x to the power of m and cos x to the power of n. So essentially sine x to the power of something. So we can actually resolve these integrals down into three cases. Firstly, when we have m is odd. So essentially when cos x is to an odd power. And secondly, when sine x is to an odd power. And thirdly, where both sine x and cos x are 2 even powers. So usually the first and second cases are easier to deal with, whereas our last cases over here can get a bit more complicated, not conceptually, but just in terms of the amount of working out that's required to actually get to your answer. It usually takes quite a while. So here is an example question. We have an integral of sine squared x multiplied by cos x to the power of 5. So as you can see, this is an example of our first case. Yeah, so we have cos x to the power to an odd power. So how we can actually approach these sorts of our first case over here is to actually apply the substitution u is equal to sine x. And so it follows that du is equal to cos x dx, as we've written up here. Yeah. So as you can see, we've actually taken out a power of cos x so that we can rewrite this cos x dx into du. Yeah. And then we are applying the substitution u is equal to sine x. So our sine x squared becomes u squared, whereas our cos x to the power of 4 becomes essentially sine x squared, 1 minus sine x squared to the power of 2. Yeah. And now what we actually end up with would just be a simple polynomial, yeah, that we can expand and then solve quite easily. All right, here is a second example where we have sine x squared and cos x to the power of 4. And in this particular scenario, we know we are dealing with the third case where both m and n are even, right? So both sine x and cos x are 2 even powers. So in this scenario, we actually need to apply these two identities over here, which we've done in the first line over here. Yeah, so we are applying those identities to rewrite sine x squared and cos x to the power of 4 so that they lose their powers. Yeah. So once we expand this expression over here, we actually end up with quite a complicated integral over here. But if you have a look at each term, the one over here and the cos 2x are actually quite easy to integrate. So what's actually causing these problems would be this third term and the fourth term over here. And what we actually need to do for our third term over here is to realize that this is, again, an even power of cos. So we actually have to reapply this identity for us to be able to solve this integral. So as you can see, it does get quite complicated. Whereas for our last term over here, which is an odd power of cos, now if we go back to our three cases over here, that tells us that we have to use case number 1. So the substitution u is equal to sine x. So as you can see, it does get quite complicated. So we've actually omitted the steps to actually integrate the third and last term. But essentially, we're just reapplying the exact same principles, which we've summarized in the previous slides. Moving on, another form of trigonometric integrals that we usually see would be integrals of this form, where we have sine mx cos nx, or cos mx cos nx, or sine mx sine nx. Yeah, so these types of integrals are usually comparatively more easier to deal with. So essentially what we need to do is to actually split them into two trig functions so that we can integrate them separately and so that they're more easier to deal with. So as long as you remember to apply these identities, you should be fine with these types of integrals. Lastly, we have some additionally important identities. in terms of tan x and sec x. So we have an example question over here where we have to integrate sec x to the power of 4 multiplied by tan x. And how we can do that is to think of how can we apply these identities to actually transform this integral into something that we can integrate more easily. And in this particular case, we actually want to turn it into the form fx, some function to the power of n, multiplied by the derivative of that function. As you can see, this is an integral that we are quite familiar with. Yeah, and how we can actually do that is to apply this third identity over here, using the fact that the derivative of sec x is equal to sec x tan x. Yeah, so this is what we've done over here. So we've taken out 1 power of sec x and multiplied it by tan x, so that gives us what we want on the right hand side over here. And taking the derivative, taking the substitution u is equal to sec x, we end up with this particular integral over here, which, as you can see, is quite easy to deal with. All right. Moving away from trigonometric integrals, we now have reduction formulae. So reduction formulae doesn't really have too much theory behind it, so we're just gonna practice looking at reduction formulae using the example straight away. Right, so this question essentially just says, let Rn be defined as this. So part A, find a reduction formula in terms of In minus 2. So with this kind of question, it kind of really comes down to practice. So in this particular case, a hint that they've given you in the question is that the reduction formula that we will eventually end up with is actually in terms of In minus 2. So essentially in terms of this integral over here. So what we can actually try to do in order for us to solve this particular integral is to actually split our tan x to the power of n into tan squared x multiplied by tan x to the power of n minus 2. And then applying our identities over here, we might get somewhere. Yeah, so this is what we have in mind, and this is what we tried to do. And it turns out to be correct as well. So as you can see, we're splitting it first to separate or isolate that tan x squared term at the start. And then using our identity, tan x squared is equal to sec x squared minus 1. Yeah, so we're going from here to here. Yeah, and we can actually expand this so that we end up with this term over here, which is exactly what we want. Yeah, and this term is actually easy to integrate because of this identity. Yeah, so you really have to be familiar with all your trig identities in order for you to see the pattern in reduction formulae straight away. And so you actually end up with this expression over here as your final answer. Now, part B, we want to use the reduction formula that we just got. So In is equal to In minus 1 minus In minus 2. So we want to use this, what we got in part A, to work out the value of this integral 10 to the power of 5, which is essentially just I5. So how we can do that is actually first to write an expression in terms of I5. And then secondly, because as you can see, I5 is in terms of I3, so then we want to write an expression in terms of I3, which is already reducing our power down to 1 already. So we end up with I1 at this stage already. Now, you don't actually have to evaluate I1 and then I3 and then substitute that into I3 to evaluate I5. A technique that you can use is to rewrite the second expression in this form. Yeah, so you end up essentially just multiplying both sides by -1. And what you're going to notice is that if you add this equation with this equation, the negative I3 on both sides will actually cancel out. So what you're left with is an expression of I5 in terms of I1 alone. So you only have to really evaluate I1 in order for you to get I5. Yeah, so that saves you the time in evaluating I3. Now this example is not too long, but when it comes to, for example, I7 or I9, this becomes really useful. As you can see, this integral here is quite easy to evaluate, and you should get half natural log of 2 minus 1 on 4 as your final answer. Then moving on to the next type of our integrals, we have integrals that involve trigonometric or hyperbolic substitution. So this is a table that kind of summarizes whatever substitutions you need to use for each integrating factors that you might encounter. Yeah? So trigonometric or hyperbolic, it doesn't really matter. Whichever one you feel comfortable with, you can substitute it into. All right. So this is our example question from a MATH1231 exam. So the question just says, show that the area A of a planar region between the lines x is equal to -a on 2 and x is equal to a on 2, bounded by the ellipse, which is given by this expression over here, where both a and b are greater than 0, has the form KAB. Yes, so k over here is a constant. And then the next thing we want to do is actually to find the value of the constant k. All right, so if you remember how we can actually find the area of a region, use integration. Yeah, so if we actually rearrange this expression so that we end up with y as the subject, we have y squared on b squared is equal to 1 minus x squared on a squared. And so y would be equal to BA, a squared minus x squared. Yeah? So, yes, exactly. So the whole point of this question is that this particular integrating factor should look familiar to you because we already learned about the substitution that we can actually use to solve. Yeah, so that's talking about this first row over here. So we can either use the trigonometric substitution of x is equal to a sine theta, or we can use the hyperbolic substitution of x is equal to a tan h theta, whichever one you want to use. So in this case, we've used the trigonometric substitution. So let x is equal to a sine theta. So as you can see, once we get that expression in terms of y, if we want to calculate the area, essentially it's just a integrate lower bound, upper bound, and then the function. Yeah, so that's exactly what we have here. We just substituted the y into the integral already. And then using the substitution over here, we can actually just simplify this using our trigonometric identities done into a cos theta squared. Yeah. And don't forget, we have to change up our upper and lower bound as well after we've used the substitution. Yeah. And then everything else becomes quite easy to deal with. So as you can see, again, over here we have an even power of x, yeah, which is essentially the first thing we talked about for this topic. So we have to use this identity to get rid of the power. And then it becomes a lot more easier to integrate. So applying the upper and lower bounds, we just end up with this particular expression over here. And going back to the question, this is exactly what we want because we want the final answer to be in the form of KAB, where K is a constant. And obviously, this scenario this term over here is a constant k. Yeah, so we've essentially proved that the area over here is in the form of KAB, and we found k to be equal to this particular value. Right, so that brings us to the end of the second topic, yeah, integration. So now moving on to the third topic, which is quite long, we have ordinary differential equations. So just an overview of the types of ODEs that we will be covering today. Firstly, we're starting with separable ODE, and then we have first order linear ODE, we have exact ODE, and then lastly we have second order linear ODE. And specifically for the last type of ODEs, we have the homogeneous case as well as the non-homogeneous case. Yeah. So starting off with separable ODEs, essentially separable ODE is where both of the variables involved can be separated fully into two halves of the equation. So in other words, it can be written in the form of this. So usually separable ODEs are the easiest type of ODE to solve. For example, this one over here can clearly be rearranged into two functions, because we can just have gx is equal to x to the power of 4, and we can have hy being equal to 1 on y squared. Yeah. But the difficult part about separable ODE is that it's not usually immediately obvious how you can actually rewrite the ODE that we've been given into this particular form over here. Yeah, sometimes it requires substitution or a little bit of manipulation or algebra. So as we can see with this particular example over here, so immediately it doesn't really seem like a separable ODE. It seems like you can write it in the form that we've talked about above. So what we actually need to do in order for us to see that this is actually a separable ODE is to use a very specific substitution. Yx is equal to x multiplied by ux, where ux is essentially just another function in terms of x. And as we will see in our next slide, after we've applied this substitution, then it becomes obvious that we are left with a separable ODE. So firstly, what we want to do is to rewrite it in terms of y on x. Yep, so essentially the general rule of thumb is that if you can rewrite this particular function in terms of y on x or x on y, then you will be able to use the substitution over here to actually rewrite it in terms of something that's a bit more easier to deal with. And remember, this particular concept of using substitution to actually solve ordinary differential equations is only examinable in MATH1231. Yeah. So, and sometimes they tell you the substitution as well, so it becomes a lot more easier. But obviously not in this particular case. Right, so if we apply this substitution, yx is equal to x multiplied by ux, then what we can do is to rewrite dy dx into d dx of xu, yeah, because we've applied the substitution over here, and then applying the product rule, we end up with this expression over here. So what we can do is to actually replace the left-hand side over here by this expression. Yeah, so which is what we did on the next line. Right, then this particular right-hand side of the equation, we can also simplify using the fact that y is just equal to xu. Yeah, so if we have y on x, and if we make this substitution, then that becomes xu on x, which is essentially just u. Yep, similar thing with the second term over here. So we can actually replace this right-hand side with u minus u squared. So now we have a function that's entirely in terms of u and x. So we have u plus x du dx, which is what we got for the left-hand side, is equal to u minus u squared, which is what we got on the right-hand side. And if these u's cancel out, hopefully you can now see that we did end up with a separable ODE. Yeah? So this is what we end up with. And we can rearrange so that all the u's are on one side and all the x's are on the other side. And so this becomes a function that's very easy to solve. So we end up with 1 on u is equal to the natural log of absolute x plus a constant of integration c. And reapplying the substitution so that we get the expression back in terms of x and y, we just end up with our final solution over here. Yep. All right. Moving on to our second type of ODE, we have our first order linear ODE, which is essentially just in the form, in this particular form over here. So this is a simple example of our first order linear ODE. So just a quick recap on how we can solve first order linear ODE. Essentially, the most important thing is to get to this integrating factor, which we can evaluate by e to the power of fx. So fx is the function over here. E to the power of the integral fx dx. Yep. And the reason why we use this particular integrating factor, which we will multiply, which we will have to multiply on both sides on our ODE to get to our solution, is because we are trying to manipulate the equation so that we can apply the reverse product rule. Yep. So if you want more detail, you can always refer back to your course notes. But essentially, we want to be able to rewrite it in terms of this particular expression over here, which, as you can see, is the product rule. Yeah. So the derivative of hxy is essentially just equal to dy dx multiplied by hx plus y multiplied by dh dx. Oops. dh dx. Yep. So the whole purpose of having that integrating factor is so that we can rewrite our ODE in terms of this, which then we can solve easily by integrating both sides. Right, so here is an example of our first order linear ODE. The first thing we want to do is to prove that what we're dealing with is indeed a first order linear ODE. Yeah. So what we can do is to rewrite it in the form that we want, which was plus fxy is equal to gx. Yeah, so we want to rewrite it in this form first so that we can apply the systematic techniques that we talked about on the previous slide. How we can do that is to divide both sides by this term over here so that we make or we isolate this dy dx over here. So we want to divide everything by this term. Yeah. So that's what we've done over here. So the first thing we want to do is to express the ODE in the proper form. Now the next thing we want to do, remember, is to get to the integrating factor, which we can get using this particular formula over here. This is just some substitution, so it shouldn't be too bad. So in this case, our fx is just equal to this. So essentially, our integrating factor h will just be equal to this, which just gives us the natural log of x minus 1. Yeah. So once we have the integrating factor, things become a lot more easier. So we can just multiply both sides by the integrating factor, and then that simplifies to us by using, very importantly, the reverse product rule, this line over here. Yeah. And then we'll just integrate both sides with respect to x to get to our final answer. So integrating both sides with respect to x, we get to this expression over here. And now, importantly, always check, because in this particular question, they've actually given you an initial condition as well. So you can't actually stop here, leaving us with a constant of integration. So we actually have to substitute this initial condition back into the question. Y0 is equal to 2. And then we get C is equal to 8. Yeah, leaving us with a solution that's independent of any integration constant. All right, moving on to our next type of ODE, we have exact ODE, which are in this particular form. Yeah, as a quick revision. So essentially, this comes from the fact that with exact ODEs, there exists a particular function h, which in this case is also the solution, such that the partial derivative of h is equal to f, and the partial derivative of h with respect to y is equal to g. Yeah. So again, the proof is in the course notes. So if you want to refer back to in case you forgot how we actually got from these definitions of exact ODE to the test for our exact ODE, you can always refer back to the course notes. All right. So again, whenever we see a question and we want to apply our technique of solving exact ODE, what we need to do is to first rewrite it in this form, or in this particular case, we actually have to apply this particular test, yeah, to prove that we are indeed dealing with exact ODEs. And then we can apply these systematic techniques that we use to solve exact ODEs. So here's an example. So the question already tells you that it's exact ODE, and all you have to do is to show that it's the case. So essentially, we just doing some rearrangement, multiplying both sides by this denominator over here, and you should get to an exact ODE. Yeah, and you have to check whether that's true by taking the partial derivative of f with respect to y and taking the partial derivative of g with respect to x. Yeah, to prove that they're equal, and hence this is indeed an exact ODE. So what's the next thing we do? Yeah, a very specific technique that we apply to solve exact ODE is we use the fact that for all exact ODEs, there exists a function h such that dh dx partial h partial x is equal to f. So partial h partial x is equal to f, and also partial h partial y is equal to g. Yeah, but we know what g and we know what g and f are, so we can substitute them into our expressions over here. Now, if we want to actually get to our function h over here, what we can do is actually to integrate both sides with respect to x for the first part, and then with respect to y for the second expression over here. Yeah, so if we integrate this with respect to x, then we will get this particular expression over here. Notice how this constant c1 over here is a function in terms of y. Now, the reason behind this, if you forgot, is because when we're integrating something with respect to x, we are essentially treating all the y's as constant. So we might actually get a constant in terms of the variable y. So that's why we have to take into account that possibility by writing the constant as a function of y. All right, we can do the exact same thing for our second expression over here. So this is our expression 1, and we've integrated expression 1 with respect to x. Now we're doing the exact same thing with expression number 2, where we are essentially integrating both sides with respect to y. And as you can probably guess, we will also get a constant, but this time we will get it in terms of x, because we are taking all the x's as constants in this particular case. Right. So if we scroll down, yeah, so that's exactly, basically we end up with the same expression. but with a constant in terms of x. Now that we have our expression number 1 over here and our expression number 2 over here, and both of them are equal to a function h, what we can actually do to get the actual solution to our ODE is to compare these two expressions. So if you have a look with our first expression over here, if we compare it against the second expression, we are actually missing a y squared, and we're also missing a y. So that tells us that our C1 in terms of 1, so our constant in terms of y, is equal to y squared plus y. Similarly, if we compare our second expression against the first expression, we're actually missing an x squared plus x. So that suggests to us this particular constant is probably in this particular form. So now if we combine these two expressions, what we actually end up with is our complete solution of h. Yeah, so we have both x squared and y squared, or we have both x and y. So this is actually the solution to our exact solution, our exact ODE. So we have h xy is equal to c, where the value of c is dependent on initial conditions. But in this case, because we have not been given our initial conditions, so we can just leave it as that. All right. Now, due to time concerns, we will probably skip this example over here, but essentially it's the exact same thing. Yeah. First, proving that it's exact, and then writing two expressions. So partial h, partial x, and then partial h, partial y. And then we want to integrate them with respect to x over here, and with respect to y for our second expression. And then comparing against these two equations, we should get our final solution, which is our function h. Right, so moving on to the last type of our ODE, we have our second order linear ODE, and we have both the homogeneous case as well as the non-homogeneous case. So to cover the homogeneous case first, so a second order linear ODE is homogeneous if it's in this particular form. Now we will see a bit later that if it's non-homogeneous, the only difference is that instead of the 0, we have another function. Yeah? So that's the only difference. All right, so with our second order linear ODE, the way we approach these kinds of questions is that we substitute in this particular solution. And where the solution comes from, or why we've chosen to actually substitute this general solution into our equation, is because we're trying to look for a function that doesn't change too much upon differentiation. So as you can see here, we want all of these terms to cancel out to give us 0. So it makes sense that we want some function y that doesn't really change once we've differentiated once and once we've differentiated twice. So we want a function that doesn't change too much, so that when we add all these terms together, we still end up getting 0. And the natural thing to think about would be exponential. Yeah, because exponential, for example, if y is equal to a e to the power of lambda x, if you differentiate it with respect to x, you just get this. Yep. And all of these are just constants. So as you can see, it doesn't really change much upon differentiation, which is ideal to solve our second order linear ODE. So if we substitute this hypothesized general solution into our second order linear ODE, what we're going to get is this particular equation over here. And if you have a look, it actually, all of these can actually be divided, right? If we divide our solution on both sides, we actually end up this particular equation in terms of constants only. So this is what we call a characteristic equation. And whenever you say second order linear ODEs, the first thing you want to do is to solve its characteristic equation. Yeah. All right. So with our second order linear ODEs, specifically the homogeneous case, we have three particular cases. So remember our characteristic equation over here in terms of lambda is essentially just a quadratic. So with quadratics, we know that we either have two distinct real roots, we have one repeated real root, or we can have two complex conjugate roots. Yeah, so that's the only three possible cases for our quadratic. So we have a distinct form of general solution for all three cases, which we've written up here. Yep. And let's say how we can apply this through an example. So first of all, you should have immediately realized that this particular equation that we're dealing with is a second order linear ODE, and specifically because we have that 0 on the right hand side, that tells us that we're dealing with the homogeneous case. Yeah. So how we can solve this particular ODE is to first solve the characteristics equation, which is given by this. So remember, this constant over here just comes from here, and the 9 over here just comes from here. Yeah. Right. So if we actually solve this quadratic, we will get a repeated root of -3. So it makes sense for us to use this particular general solution that we had. Yeah. So if we write it out, and then substituting in the initial condition, so y0 is equal to 0, we will actually get that a is equal to 0. Yeah. And then, so the first term will just disappear, and we end up with a general solution that's essentially y is equal to bx e to the power of -3x. Right. Part B, for what value of x does the solution have a maximum? Essentially, because we've already got this solution, the general form of solution, how we can actually find the maximum value is essentially to use the idea of differentiation. Yeah, if we take the derivative, and when the derivative is equal to 0, then it tells us that the solution has either reached a maximum or a minimum. So in this case, when dy dx is equal to 0, we have x is equal to a third. Yeah, so that's where our solution will actually obtain maximum. Now with the non-homogeneous case, as I've talked about, on the right-hand side instead of 0, we have another function, fx. So the non-homogeneous case is not too complicated as well. Essentially, again, to solve the non-homogeneous case, you actually have to find the homogeneous solution first, which is denoted by this YH over here. Yeah, so it's essentially just imagining this as a 0. Yeah, so you have to find the homogeneous solution first, and then you have to find what's known as a particular solution, YP. Yeah, and then you add them together to find your actual solution. Now with your particular solution here, there is actually some degree of guesswork involved. So particularly if we have a look at this table over here, yeah, our guess for our particular solution YP actually depends on the fx, which is on the right hand side of our equation. So you can always refer back to this table. It's in your course notes as well. So essentially, for example, how I read this table is if your fx, so your fx, which is this, on the right hand side over here, is a polynomial of degree n, then your guess for the particular solution will be another polynomial of the same degree n. Yeah, does that make sense? But the only thing that you need to be aware of is once you've obtained your guess for your particular solution, what you always need to do is to check if your particular solution over here is already part of the homogeneous solution. Now, if it is, then you want to multiply it by x. Yeah, and if that particular expression that you got is still part of the homogeneous solution, then you have to multiply it by x once again. So that's probably the most crucial thing to remember for solving second order linear ODEs. Right, so again, due to time concerns, we will probably just very quickly go through one particular example question. So here we have maybe this one. Yep. So here we have a second order linear ODE. Yeah, as you can see on the right hand side, we have a function that's non-zero. So our natural next step is to firstly remember find the homogeneous solution, and secondly find the particular solution. And with the particular solution, because we have this particular exponential function, what we want to do is to actually guess using our table over here. So because we have this particular second row over here, so our first guess would be to take a polynomial of the same degree and multiply it by the same exponential. So our first guess would be to have a constant multiplied by a to the negative x. Yeah, so let's have a look at the solution. So as always, the first thing we do to find the homogeneous solution is to solve the characteristic equation, as we've done over here. And it turns out we actually have a complex root, which is the case that we've talked about but have never practiced on. So the general solution over here is a bit different. Yeah, you can always refer back to the previous slides to have a look. But with complex roots, this is the general solution that we use. Now the second step is to find the particular solution. Now in this case, as you can see, our guess for the particular solution is just ax to the negative x, sorry, ae to the negative x, which we talked about over here. And then we differentiate it once, differentiate it twice to get the derivatives. And then once we've substituted all of these back into our ODE, yeah, we can actually cancel out these terms to realize that our a constant over here is actually equal to 2. And so as a result, our final solution for our ODE is just equal to the homogeneous solution over here plus the particular solution over here. So it becomes this plus replaces a with 2, which we've just evaluated. We end up with this particular expression as our final solution. Right, so we have one more question over here, but because it's 4:03 already, remember these slides will be uploaded, so if you're interested in having a go at these questions, you can always download the slides and then have a go yourself. And the solutions are all written down here as well. So I will now pass on to our second presenter, Wendy, to take you through the last two topics.
Hello. Is everything good? Am I audible? Am I screaming into the void? Nice, nice. I know there's like a 10-second delay, so this is gonna respond. I'll try to, actually leave time for you to type things, and I don't get impatient about it. Anyway, we are okay. So I am technically going through Taylor series and applications integration. That's the topic name, but the true meat of today is convergence. Let's be real. So going through firstly applications to stationary points. It's quite interesting. You got the usual application. Your first derivative is 0. You're like, aha, stationary point. And then second derivative is positive or something. And you're like, hey, minimum turning point. So this test is actually nice little expansion on that. So what happens if you find your first and second derivative and they're just both 0 and you keep differentiating and it just keeps being 0? This test just keep differentiating. At some point, hopefully, you'll hit something that's not equal to 0 when you actually sub it into this mysterious kth derivative. And then from this kth derivative, so for example, in this first condition over here, if your k happens to be even and that number you sub in, so you sub in a into that kth derivative and it's positive, then you say that original a, that's a local minimum point, even if your second derivative was 0. And the other conditions follow. You get a local maximum if k is even and the number's negative, and you get a horizontal point of inflection if k is odd. It's quite a nice test, but yeah, it's kind of a niche thing. It's a nice test, but there's not a lot of examples on it. But we appreciate it. Okay. Oh yeah, if you have any questions, just like pop them in the chat. But there is a bit of delay, so I'll probably respond in a weird time duration. Okay. Firstly, going through sequences. So we start with the definition of a sequence. So easiest way is probably just to look at a sequence. So like here we have an example, an is equal to n squared. That's an example of a sequence. So like a1 would be 1, a2 would be 4, a3 would be 9. And your sequence would just be 1, 4, 9, 16, 25. So a sequence is just a function taking in natural numbers. So that would be, for example, just 1, 2, 3, 4. And then it pops out real numbers. So with the example I just said out loud, those would be the 1, 4, 9, 16, 25. So you just take in whatever you need to. Sometimes the sequences start from n equals 0. Sometimes they start a bit later. But it's the natural numbers. You start from the domain. Then you get into the real numbers. They can also be defined a bit more fancily. An equals the sum of the previous two terms. But yeah, ultimately sequences just taking in natural numbers and popping out some real numbers by whatever rule happens to be dictating that sequence. More relevant, well, not more relevant, but what the major thing we're going to do with sequences, convergence and divergence. So you have a sequence, like, say you have that square number sequence, the 1, 4, 9, 16, whatever. And you wonder, is this convergent or divergent? Now, this is relatively, you can tell what they mean by their name. So a convergent sequence, eventually, when you get it into n approaches infinite, it will approach some finite number. So basically any number that is an infinity. So your square number thing clearly just shoots up into infinity. It's not going to approach some finite number, so it's not convergent. It falls under the divergent category. And then you can further classify the divergence. So you can diverge to infinity, diverge to negative infinity, relatively self-explanatory, those ones, like the square number things goes off into infinity. Then you have the boundedly divergent and unboundedly divergent. So the boundedly divergent sequence is most clearly explained by the sine function. Sine function, bounces around between the 1 and negative 1. Ultimately, when you go off into infinite, you don't know whether what number it actually approaches, because it's still just going between 1 and negative 1. But you do know there's a bound on it. It's not going off into infinite. There's a specific set of numbers it could possibly be in at infinite. I don't know what it is, though, so boundedly divergent. And then unboundedly divergent is just whatever doesn't fall under the first three categories. And if your thing is dictated by a function, so we had previously an equals n squared, so f of n would just be n squared in that scenario. If your an equals the same function for all large n, and the limit of this function as it goes to infinite exists and is finite, so basically it's not infinite, then the limit of your sequence as n goes to infinite is equal to that same limit of the function. Yeah, that one, I hope you'll just accept that in your soul. But yeah, so let's get into a very, very nice example. We have, from the Hallowed 2016 paper, determine whether this sequence converges or diverges as n goes to infinite. So, once you could try. Probably the question wouldn't be that easy, but you should try to slap an infinite just to check whether you can see what it diverges or converges to. Slapping an infinite here doesn't really do much for you, because you end up with the square root of infinite minus the square root of infinite. You can't compare infinite like that. So what you're going to do instead is a beautiful technique known as multiplying the numerator by the conjugate. I say numerator, but pretend, I mean, it is a fraction, it's just over 1. But multiplying the numerator by its own conjugate. So here the quote-unquote numerator, square root n plus square root n minus square root of n, its conjugate, there it is. Its conjugate, fudge me. Okay, its conjugate is square root n plus square root n plus square root n. So just that sign between the two surds there, just swap it out from a minus to a plus. Multiply that to the numerator and denominator, because if you just multiply by the numerator, you'd be changing the entire fraction. But the whole point of doing this unusual multiplication is so that your numerator simplifies really nicely. Like, look at that numerator. It's just root n now, via the power of difference of two squares. If you try subbing in infinite, you're still not going to have much going for you, so we'll have to keep going. What we're going to do is then just divide by square root n to numerator and denominator. So you see your numerator just pops out to being just a 1. And at this stage, if you try and subbing in infinite, you'll see that this 1 over square root n just goes off to being 0, and everything else is a nice constant. So you just have 1 over 1 plus 1, and it's half. So that's, you do keep on trying to type in infinite to see whether you get a nice number yet or not, whether you can, by nice number, I don't mean finite. Like, if you prove it's infinite, that's fine, it just diverges. But you do have to be able to evaluate it. So you can't evaluate things like before with square root infinite minus square root infinite, but you can evaluate this. And since it's half, that's a clearly finite number. So your sequence converges to half. And yeah, convergence, very nice. So if you got any questions about the what it means for a sequence to converge or diverge, just pop that in the chat while I move on to the sequences further. Combining sequences. This one's pretty alright. Pretty sure everyone just accepts this. You can add sequences together. Like if you had a square number sequence 1, 4, 9, 16, so they're described by the n squared, and you had the cubic sequence, the 1, 8, 27, 64, and that was n cubed. They would be the same as the n squared plus n cubed sequence if you added those two sequences together. And you can do that to multiplication and division. If your sequences are both convergent, then you can also apply this technique of adding, subtracting, multiplying two sequences together to their limits as they go to infinite. So you have an and bn. If they converge, if those two sequences converge, you can take n approaches infinite, and then an times bn is the same thing as if you evaluated those two limits separately and then multiplied to get that together. So yeah, that's a nice little, you can apply operations to sequences. I suppose this is not biased. This is very important. Order of growth. So what the elementary functions is just like the power functions, trig functions, log functions, exponential functions. So order of growth of these. So basically, how fast do they increase? So if you picture the first one, the constant is relatively, you look at it, it's just, that's a terrible graph. Pretend I know how to draw horizontal lines. Let me just, cool, good enough. Constant doesn't change, always the same value. Its growth rate is pretty, it's not as bad as my marks, but its growth rate is pretty bad. Now the log function, hopefully you remember, beautiful log function, bam, it grows, definitely grows at least, but it's not that fast of a growth. You can already see it shallowing out, as opposed to the power functions. So you have n to the power of k, so that'd be like n squared, n cubed, that looks like that kind of thing. You'll see growth rate much faster than the log, and that's what this whole table is, just all those functions get faster as you go down the table. So the next one is the exponentials. They are faster than your powers, your factorials faster than your exponentials, and your n to the power of n is faster than your factorials. It's a very nice order of growth table. And you just let that knowledge sink in, let the order of growth sink into your soul. And yeah, you just let it sink in. Don't worry about needing to prove that one. Just use it when you need to. Now, for the sequences, we're still in sequences. We'll get to the series one day. Suppose that you have these three sequences, a_n, b_n, cn, and that for some integer, capital N, above that integer, all the terms of your sequences, the a_n, b_n, cn, they satisfy this inequality. So the a_n terms are less than or equal to b_n terms, less than or equal to cn terms. And if this works, then you can use the pinching theorem. If you find that a_n and cn both converge to the same value L, then bn converges to that L. So, two terms around a middle term, if they all go to the same number, and they pinch that middle term. It's a nice name. But yeah, that's a nice little test there for the convergence. So you don't have to worry about whatever weird sequence bn was if an and cn manage to be really nice things to evaluate for convergence. Pinching theorem. Also keep that in your mind. There's a lot of things you got to keep in your mind. So thank the open book. I definitely have notes open somewhere. Now this one. This one is reserved for the 1241 elite. So if you're 1231, you should still listen anyway, because math is fun. All right. So we have another test for convergence. Now this test firstly relies on you knowing what the monotonic definition is. So monotonic sequences are either increasing, non-decreasing, decreasing, or non-increasing. It's a lot of categories, but ultimately it just means your function doesn't do increasing and decreasing. So your function doesn't go blah, 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 blah. If your function just maintains increasing the whole way through, and by things like non-decreasing, it just means that it increases or it's stationary. So like that. So basically means it never decreases. So it's still monotonic. So if your sequence satisfies that, then, well, actually not then, sorry, we'll get to that theorem later. A few more definitions. A sequence is bounded above if there exists a capital M such that all the terms of the sequence are less than or equal to that capital M. So, bounded above. The M is above all. And bounded below if all the terms of your sequence are greater than or equal to some mysterious capital M. So those are nice three definitions there: monotonic, bounded above, and bounded below. Now what to do with this? If your sequence is a bounded monotonic sequence of real numbers, then it converges to some real number L. Then you can go ahead and just slap that theorem down. The real number bit is important. It does have to be in the real numbers. But other than that, it's a pretty nice condition to use to try and prove convergence. So if it's bounded and monotonic, bam, converges to some real number L. Now supremum and infimum, also 1241, but keep listening. It's really great. So the supremum M of a sequence is a sequence's least upper bound. So upper bound, it's all those numbers that are greater than or equal to the elements of your sequence. But the smallest of those numbers becomes your supremum. Infimum, similarly, there's a bunch of numbers that are less than or equal to the elements of your sequence, but there's this particular one that's the biggest out of those numbers. And if you find the supremum and infimum, what you can do, so the least upper bound axiom, every non-empty set of real numbers that is bounded above has a least upper bound. It's very nice. But also, real numbers, pretty important. So if you have a bunch of real numbers and it's bounded above, then it has to have a least upper bound. In other words, it has to have a supremum. So that's neat. Also let that sink in. So now I will get into a beautiful example of finding the supremum and infimum. We have these two sets over here. So the first one, n over 1 plus n squared. Where n is equal to 1, 2, whatever. So this is one of your typical sequences. You've got the input, the 1, 2, 3, 4, whatever natural numbers. And once you slap, for example, put the n equals 1 in, you'll get 1 over 1 plus 1 squared. So half, bam, output. You have a real number. So that's a nice little sequence there. Now, if it has supremum and infimum, so you can try subbing in those 1, 2, 3s. I mean, that is one of the, it is a good method, to actually test out some things. You'll see that this fraction just keeps decreasing. So 1 over 1 plus 1 squared, that's half. And then you try subbing in 2 over 1 plus 2 squared. That's 2 over 5. And it'll just keep getting smaller the more numbers you sub in. And eventually, as n goes off into being infinite, this whole thing approaches 0. If you've forgotten about how to, do that just by the, embracing the soul of mathematics, if you have a ratio of polynomials and the degree of your numerator is smaller than the degree of your denominator. So in part A, you'll see here, you'll see that's degree 1 in the numerator, and you'll see that's degree 2 in the denominator. So when you see that numerator degree is smaller than a denominator degree, as n goes off into infinite, the whole thing approaches 0. If you don't know that, go ahead and know that, memorize that. So that's very useful for this question. This thing starts at half and then just goes off to 0 as n goes into being infinite. So that means you can work out the supremum and infimum. It's never going to go below 0. It's never going to dip below that. So its infimum is 0. That's the biggest of the numbers that are smaller than all the elements of a sequence. And its supremum is half, since it starts at half and then just keeps decreasing. So all the numbers that are greater than or equal to the element of your sequence, half is the smallest out of those ones. Even when half is included in the sequence, it's still your supremum. Part B, you have part E, sine x is less than 0, x belongs to 0 to infinite. A bit of a funkier looking sequence. To find those values of x for your sequence, when sine x is negative, recall the beautiful sine graph. Sine x dips to being negative when x is from pi to 2 pi, but exclusive, or it's from the, it is from the, 3 pi to 4 pi, or it is from, it just keeps going, because sine is periodic, of course. If something's true for that interval, it's going to be true every interval of 2 pi. So 5 pi, 6 pi, etc., keeps going. So those are the values of x that could fit the sine x being negative and still fit the x belonging to 0 to infinite thing. It doesn't have a supremum. Like, x just keeps going. Like, x goes off into being infinite, just forever. So you can't say there's anything, there's no numbers that are bigger than or equal to the elements of your sequence. Your sequence goes off into being infinite. So no supremum, but it does have an infimum, and the infimum is pi, because all the elements of your sequence are greater than or equal to pi, and pi is the biggest number out of all those numbers that are less than or equal to your sequence. And that's how you work out the infimum and supremum. A bit of a detour into 1241 for the 1231 people, but hopefully it's quite fascinating. Now the infinite series. So finally, getting into the difference between a series and sequence. A sequence you saw was basically like 1, 4, 9, 16. It was a list of a bunch of numbers. Your series is when you sum the elements of your sequence. So if I take my square number sequence and I add the 1, 4, and 9, suddenly I have a series. So you can add, several terms. So you have a partial thing, you just add up n terms, or you can sum up all the way to infinite, and you just have an infinite series. So you subbed every single term of your sequence all the way into infinite. Now your series also, if your series converges to L, so if that sum of all the elements of your sequence converges to some finite number L, you got the convergence, and if it doesn't, then it diverges. So yes, again, pretty similar definition of convergence and divergence, but just remember series is the sum of the elements of a sequence. And the sequence, of course, is just the elements of the sequence. Yep. Now, series, same way manipulation as the sequence. If you have 2 of these adding together, you can just split them out into the sum of 2 series. It's fine. You can chuck out some constants. It's fine. Interesting thing to note here is that because if you have a bunch of finite numbers and you add them together and it's still a finite number, then when if you're trying to find the convergence of a series, of the infinite series, you don't really have to go from 0 to infinite. Like if you prove from n to infinite and it converges to some finite number like 5, then all the things you left out, the 0 to n, they add up to some finite number out there. And then you just pop that on to the 5 you found, and lo and behold, your infinite series still approaches a finite number. So you only really have to prove, the latter bits from n to infinite. if necessary. Of course, you can prove from 0 to infinite, but that's a neat thing to note. Now here is where the end, or perhaps the beginning is. Tests for series convergence. I hope you all have these tests somewhere out, or at least you have it flipped open to your course notes section. There's a lot of tests for series convergence. Let's start off with the best test. Honestly, the Cave term test for divergence. This is pretty much the first test you should try out because it's just such a good test. You're given the sequence, and then, does the series diverge or converge? What you do, you look at the A Cave term as k goes to infinite. So, the infinite term of your sequence that your series is trying to sum. If it doesn't go to 0, then your series diverges. And that's a very powerful thing to do. It solves a lot of questions really fast if you remember it. Of course, it does have some pitfalls. This only tests for divergence. So if you prove the AK doesn't go to 0, you're cool, it diverges. But if you prove it does go to 0, you're not allowed to say it converges. It could still diverge. You don't know what's happening. You have to resort to other tests, which we will go through. So it's really important to remember that this only works for proving that divergence there. Also a theorem to note is if they tell you the series converges, then you can say AK goes to 0 as k goes to infinite. But you can't prove AK goes to 0 as k goes to infinite and then say it converges. So just be careful about the direction of these stuff. Now, another, number 2, another test for series convergence is the comparison test. Suppose that you have these two sequences, the AK and BK, and you know AK is smaller than or equal to BK for every natural number k. So, n squared and n cubed. Yeah, n squared always less than or equal to n cubed. Cool. Now, if that bigger sequence, that BK, if its series converges, then you'll know that AK converges, since NK has to be less than or equal to that BK one. Don't take that. Proof for that is much better than me just saying that. But it's a good way to think about it intuitively. And if AK diverges, so the sequence below the BK, if it shoots up, then your BK, not shoots up. If it diverges, then your BK also diverges, being above that AK. And that's pretty good. That's a nice series. That's a nice test for convergence for series to remember. It's known as the comparison test. You also have a P-series test where if it's a pretty specific sequence, but you'd be surprised how often you come across it. If you have 1 over k to the power of p, and you're trying to sum this infinite series, proving you're trying to sum the sequence, so it's the infinite series. It will converge if p is bigger than a 1, and it will diverge if p is less than or equal to 1. And all you have to do is examine the p. So it's a very fast test. It's very, selective test. It only works for this series, but very powerful if you ever got a question on that. Now going through a beautiful 2018 paper example. So you have your infinite series. Don't know what it is, but you know it's convergent because they tell you so. They also tell you every term is positive for all n, and that'll be important later. Firstly, part A, state the limit of an as it goes to infinite. Now, of course, I just realized you can see the answer right there, but you weren't looking at that. You remembered the previous slide. And you know that if you know an infinite series is convergent, then AK has to go to 0 as k goes to infinite. Well, in this case, it's an. An goes to 0 as n goes to infinite. And that's just the privilege of knowing that it's a convergent series. Part B, using the nth test. It is just a Cave term test. It's called the nth term here because, an, not ak. But use the nth test to show that the infinite series long of an diverges. Remember what the nth term test here, remember what that is. If your an doesn't go to 0, then you know that it diverges. They already tell you to show it diverges, so you already know. You've got to prove an doesn't go to 0 as n goes to infinite. And lo and behold, if the limit of an is 0 as n goes to infinite, then the limit of long an has to be negative infinite because long of 0 is negative infinite. Sorry, not long of 0, long of number approaching 0 is negative infinite. And that's clearly not 0. So your sequence diverges by the Cave test. I should have changed that to nth test. You didn't see that. Part C. Given that your f of x is equal to x minus ln 1 plus x, they tell you it's positive for x being greater than 0. Determine whether or not the infinite series long of 1 plus an converges or diverges and explain your answer. The long 1 plus an is, of course, really suspiciously in your f of x. It's the second term right there. So what we're going to do, your x minus long of 1 plus x, you know it's positive because they tell you so. So if x minus long 1 plus x is always bigger than 0, what we have here is that x has to be bigger than long of 1 plus x, since x minus long 1 plus x is bigger than 0. What we also know is that x is positive. So we can just swap it out for an an. It has come back to haunt you. So that was the initial question when they just had the an bigger than 0 and they just told you that and then left. So that's here where it comes in because an's bigger than 0 and that's about it. That's the only condition on the an. And in part C, they tell you x is bigger than 0. We just go ahead, casually swap out that x for an an. And we have an is bigger than long 1 plus an. And that's fine. The x satisfied the only condition we had on an. We know that the infinite series an converges because they tell us so. So by the comparison test, remember the comparison test, when you have the sequence being smaller than another sequence. So here's the long 1 plus an, smaller than the an. We already know the top one converges, and that forces the one below it, that infinite series, to go ahead and converge. And that's why long 1 plus an converges. Ayo. And that's also what they mean by like explain your answer or give reasons or something. Of course, you have to show like working, but one of the main things is naming the test. So here it is, the comparison test. Pretty cool, pretty nice. Oh, right, yes. Also, another example, just to speed run the test we just went through. So we did what have we done? The cave term test, the comparison test. Here is, I was about to just name the test and give it away, but giving brief reasons, state whether the following is true or false. You have an infinite series 1 over n to the power of s, and you know s is equal to 2 on 3. The statement is that it diverges. Is it true or false? Hopefully, you have been letting the glory of mathematics take you under. And you remember the truth. This is the p-series test. Provided there's no p, but it's you just remember you can swap out those letters. It doesn't have to be a p. So maybe I should flip back. Let me just flip back a bit. There it is, the p-series test. 1 over k to the power of p. If p is less than or equal to 1, it diverges. If p is bigger than 1, it converges. K goes from 1 to infinite. So if you compare that to the question here, with 1 over n to the power of s, and goes from 1 to infinite, s is 2 on 3, s is less than or equal to 1, therefore it must diverge via the p-series. So this statement is true. And that really is how fast the p-series gets used. It's just a really, really quick check there. It's beautiful, beautiful test. And let's keep going. Test for series convergence number 3, but only for the elite of 1241, unfortunately. Not unfortunately. Well, yes, unfortunately. But yes, 1231. Observe this anyway. It's pretty cool. But you don't need to worry about it. So we had the comparison test from before, with the whole AK less than equal to BK thing. The limit form of the comparison test, basically the advantage of the limit form is you don't have to worry about inequalities, right? Like before in the comparison test, you would have had to do a little proof there, like, oh, is this thing actually smaller than the other thing, which is smaller than the other thing? The limit form of the comparison test helps you a bit there. Suppose you have an and bn, they're both positive sequences, which just means their elements have to be positive. There's no numbers in there that are negative. Suppose that the limit, as n goes to infinite, of an over bn is equal to L, and L is some finite number, and it's not 0. So it can't be 0 and infinite, basically, all the numbers in between. If you can prove that, then, not if you can prove that, if that's true, then if the series, the infinite series an converges, if and only if the infinite series bn converges. If you've forgotten what the if and only if is, it just means it works both ways. So if you prove the infinite series of an converges, then you'll know the infinite series of bn converges, and vice versa. If you prove infinite series of bn converges, then the infinite series of an converges. If and only if is pretty powerful. But yeah, it's a very neat test just because there's no inequalities involved. You just have to find that mysterious limit out there, that an over bn that forces the L to happen. And then you can just, if one of those is a really nice convergence for an or bn, then the other one converges. So that's the limit form of the comparison test, but it's only for 1241. Yeah. Now we have another series test. How many are we up to? Right, this is number 4, or potentially number 5 if you count the P-series test as one. Yeah. So we have the integral test. The integral test, if you have the formula for AK, like before, if I knew AK was k squared, I could have just replaced it with f of x equals x squared. Go ahead and do that. If this fx function is continuous, and it's positive, and it's decreasing from 1 to infinite, there are several conditions. Continuous is, a lot of the time, it is just continuous. Positive means it has to be above that x-axis. And decreasing, of course, just means it decreases. Yep. If f of x satisfies all of that stuff, then we can apply the integral test. So you evaluate the integral. So, if you love integration, this will be a boon for you. If this integral converges, so basically if it goes to a finite number, then so does your infinite series. And if your integral diverges, so does your infinite series. It's really nice. Like, all you have to do is evaluate an integral. I say that, but sometimes that's really hard. But yeah, basically, if your f of x satisfies these conditions, you can go ahead and slap the integral test down. It's really neat. Right before we jump into example, let's squeeze in another test for series convergence. This is known as the ratio test. So you have an infinite series. It's all got positive terms. If you take the k plus 1th term over the kth term and you make k go to infinite and you evaluate whatever that happens to be, I've just realized that's a minus sign. Pretend that's an equal sign. That limit is equal to r. If r, let me just put that. That's going to annoy me for a bit. Oh, it's the worst equal sign I've ever drawn. Okay. If your r is less than 1, then your series converges. If your r is bigger than 1, then it diverges. And if your r is equal to 1, then it's inconclusive. That's kind of important. You can't just draw random conclusions if r is equal to 1. So it could converge or diverge. You don't know. But if it satisfies either of the first two conditions, then you're golden. You've just proved whether it's converging or diverging. So yeah, ratio test. So, hopefully you're compiling your list of tests. I don't really want to speed. Wait, kth term, comparison, integral, ratio, limit form of comparison, P-series. I definitely skipped over one of them. But yeah, have that list somewhere. But anyway, 2016 paper. Use an appropriate test to determine whether or not this converges or diverges. Normally, I'd let you have some time to stew over this, but looking at that, very interesting, 4:38 p.m. Here it is. It's the ratio test. So the ratio test here, remember, you take the n plus 1th term, divide it by the nth term, then force n off into infinite. So firstly, when you do a little division there, it simplifies to being this n squared plus 2n plus 1 over 2n squared, after a perfect square expansion. And this limit as n goes to infinite is half. Once again, if you've forgotten the technique for doing a subtle cheat there, if the degree of your numerator is equal to the degree of your denominator, in this case they're both degree 2, then all you have to do is ratio the leading coefficients, and that's what it approaches as n goes to infinite. So yeah, it approaches half. And that ratio is less than 1. So ratio test style, it converges. It's very nice. Next series here, 1 over k times a ln k all squared. And that looks horrifying, but integral test. So the integral test, you swap out your formula there for f of x. So now it's 1 over x ln x all squared. And you integrate from 3 to infinite. Just integrate over whatever bounds your original infinite series had. So, originally 3 to infinite. You keep those same bounds. You do a little casual u sub of the u equals ln x, since its derivative is 1 on x, and 1 on x is very suspiciously right there in your integral. You don't have to write out the explicit substitution. You can do this little thing in your head. But with the explicit substitution, of course, the bounds will change. If u is ln x, you can't use x goes from 3 to infinite. You use u goes from ln 3 to ln infinite. Ln infinite is just infinite. So that's what that upper bound there is. And then you just evaluate the integral of 1 over u squared with respect to u, becomes negative 1 over u, sub in your upper and lower bounds, and you get 1 over ln 3, which is finite. Therefore, series converges. So integral test is pretty neat. To be fair, I have also very casually skipped over the conditions. The conditions of the integral test, your function had to be positive, which x is bigger than 3. So yeah, this is positive. Your function has to be continuous. Yeah, it's continuous. It only goes weirdly discontinuous at x equals 0, and that's not an issue here. And it has to be decreasing, which is probably the more annoying one. Sorry, it is the most annoying one to prove here. I'm not sure whether you would accept, I don't think you'd accept by your heart. You can do a little quotient rule there, just to prove whether or not the first derivative is always negative. And then you prove it's decreasing, and yeah, satisfies all the conditions to use the integral test. Series test convergence number 6. So far, all the elements of your sequences have been all positive. And that's what all the tests have been for. If your series is all negative, you just take the negative out and basically you still have a positive thing left over. But if you have positive, negative, for the terms of your sequence, then you'll have to use a Leibniz test for convergence. The three conditions to satisfy. If AK is greater than equal to 0, AK is greater than equal to AK plus 1, basically means the sequence is decreasing. And the limit of AK as k goes to infinite is 0. All the AKs here are the positive versions of it. So like if this was 1, -2, 3, -4, you will be looking at the 1, 2, 3, 4 for the AK. But if you satisfy all three conditions here, you have a convergence by the Leibniz test for convergence. If you don't satisfy a condition, you can't say it diverges. It's also one of those theorems. So this only works for the convergence. If it diverges, you just have to find some... So not if it diverges. If it doesn't satisfy a condition, you have to find some other test to worry about whether or not it converges or diverges. So this one is pretty specific to convergence. Like the cave term test was pretty specific to divergence. Now, absolute and conditional convergence. A series will be absolutely convergent if you take the absolute value of all your terms. So if anything was negative, bam, now it's positive. If you prove that sequence, if that series converges, then it's absolutely convergent. If you've just proved it's convergent and it doesn't absolutely convergent, then you say it's conditionally convergent. And yeah, there are some subtle differences between them, of course. Well, not so subtle. If it absolutely converges, it converges to a specific unique value. If it converges conditionally, it could converge to any real number, depending on how you do a little casual shuffle there. So, having an example on doing absolute and conditional convergence. We have this series here. Does it absolutely or conditionally converge, or does it straight up just diverge? What are your reasons? Okay, so first you look at this series. I already given it away, but first you look at this series. It's an alternating series. Because of the -1 to the power of n, your sequence elements are actually positive, negative, positive, negative. So you just kind of straight go for the Leibniz test. Like when you see the plus, minus, you're like, it's time, the alternating series. So according to Leibniz test, you got the three conditions here. You look at the positive versions of all the terms. So 1 over n log n is non-negative for n greater than or equal to 2. So there's the first condition. Your sequence is decreasing because you'll see as n increases, your denominator increases, which actually means that your whole fraction is decreasing. So yeah, your whole sequence is decreasing, condition number 2. And condition number 3, condition number 3, if n goes off into being infinite, 1 over n log n approaches 0. So that's condition number 3 satisfied. And if all three conditions are satisfied, bam, Leibniz test for convergence, this series converges. But then we have to test for absolute convergence. So absolute convergence, when you're testing for that, basically you're just looking at this series and pretending it was always the positive version of itself. So there was never a -1 to the power of n. The sequence is just 1 over n log n. And you can use all those tests from before that we talked about. So what we're going to use here is the integral test. So when we integrate from 2 to infinite of 1 over n log n, it's the same evaluation as before. You sub u equals log n. This actually evaluates to infinite, which of course means it doesn't converge since it doesn't approach a finite number, and it fails the integral test. So it only converges conditionally. It doesn't converge absolutely because the positive version of the sequence, it just fails. And yeah, there's a difference between conditional and absolute convergence. And now I'm actually in Taylor series. But truthfully, yeah, the convergence thing, it's a very important part of this thing. Now, the Taylor series. Taylor series is a specific infinite series that looks like this. There's the sigma. You can see the formula version of it. F of... fudge me. Okay. Let me just Okay, those very bad things I put about the n, those are brackets. Okay, so there is a difference there. When you see f of a to the power of n would, look like that. But with the brackets, that means the nth derivative. So be a bit careful. When you see brackets there, it's the nth derivative and not just f of a raised to some power of n. Okay, so the nth derivative of f evaluated at a over n factorial times x minus a to the power of n. That's the general term of your Taylor series, and you can see it's expanded to the right there. You sub in n is 0, you sub in n is 1, you get all these terms starting popping out. It's an infinite sum here. You can see it goes from 0 to infinite. If you have you have a smooth function f about a, you can define it with this nth Taylor polynomial about the a. It doesn't go off into infinite. This is the nth Taylor polynomial. It's the exact same formula as before. It just stops at the end since it's the nth Taylor polynomial. And it's an approximation for the function f about the specific point a. If you try and go out any further, like if it was about the point 1, this would work pretty well for 1. It wouldn't work well if you tried to take it out like 105. You do have to be about the a. Now, the Taylor's theorem states that if your function has n plus 1 continuous derivatives on an interval containing this a, then you approximate it using a Taylor polynomial, and the remainder is exactly that. It does look kind of complicated. The 1 over n factorial integral from a to x, n plus 1th derivative of f, and you're integrating that. It's quite an interesting remainder. We do have a more simplified version of this remainder, the Lagrange form of this remainder. Oh, every time. Let me just put in that equal sign. Okay. But yeah, here's the Lagrange form of the remainder. It doesn't have the integral hanging around it anymore, but it is slightly a bit more annoying with the whole c is some number between a and x. But yeah, it does look simpler than the original remainder form. So here's the Lagrange remainder form. Sorry, Lagrange form of the remainder. When you try and use the Taylor's theorem to approximate your function by a Taylor polynomial. So yeah, the Pnx was just a Taylor polynomial, nth Taylor polynomial from before, and your Rm plus 1x, you either use this form or you use this Lagrange form. But the Lagrange form, it does look nicer. So a nice little question on this. It's really more of an application of just understanding Taylor's theorem. We have some real polynomial out there of degree n. Using Taylor polynomials, we can write p of x, we can rewrite it in this form. Explain why it's true. State the theorem you would use to prove it. Give an expression for the largest capital M such that am isn't equal to 0 in terms of n or px, and explain how the numbers ai are obtained in terms of p of x. Seems really long, but let me break it down. It's not that bad. Using Taylor polynomial, we can write this. Why is this true? Plot twist, it's true because of the Taylor's theorem. That really is the theorem that's being used here. So it's true because of Taylor's theorem. Remember the condition of the Taylor's theorem was n plus 1 derivatives. N plus 1 times differentiable. P of x is a polynomial. It's just infinitely differentiable. So that's fine. That's about it. That's the only condition you needed. Yeah, we can use Taylor's theorem, and that's why we can express P of x in this form. Then according to Taylor's theorem, which you all definitely remembered, the coefficients of those x minus c to the power of I, they're just the ith derivative of p evaluated at c over I factorial. Let me just scroll back up a bit. Yeah, there it is. The kth derivative of f evaluated at a over k factorial. Just with some little swapping out of variables. So that's pretty much a direct copy there of the ai from your Taylor's theorem. And then, of course, the question, what is the largest m such that am isn't equal to 0? Am. Just swap the I out for an m. Now, this will equal 0 if m is bigger than or equal to m plus 1. And that's more of a property which you hopefully remember, that if you have a polynomial of degree n, as soon as you hit the m plus 1 derivative and any higher, it's always going to be 0. Like picture x squared, the degree 2 polynomial. By the time you reach the third derivative, it's already 0, and it's just going to keep being 0 the more you differentiate it. So this mth derivative of p of x is just going to be 0 as soon as m is bigger than or equal to m plus 1. So the biggest m such that your am isn't 0 will happen when m is equal to n, because any higher than that is just 0. And yeah, there's that question. Haha, take that, question 6. So yeah, let the Taylor's theorem definition sink in, and everything will hopefully be okay. Now, some little special cases of the Taylor series. What I said before, the Taylor polynomial about A. So A is some number out there. But if in the particular special case, you're evaluating it around A equals 0, this is known as the Maclaurin series. So the Maclaurin series is just a special case of the Taylor series. You'll see here, this is exactly the Taylor formula, like this whole thing. That's exactly Taylor's theorem, but the A is 0. And that's just what the Maclaurin series is, subbing in A equals 0. So that's just a terminology for you to remember. We have some examples of convergent Taylor series. So all of these are evaluated using the Taylor's theorem. Like you differentiated, you can see all the factorials from the Taylor's theorem. If x falls within these domains here at the side, that's where these series go convergent. Like for e to the power of x, it's just always convergent since it converges for x belonging to real numbers. You can check, evaluate all of these using Taylor series. It is also pretty advisable for you to just start memorizing these. In higher years, they really do like to just pull out the Taylor series without really pointing out this Taylor series first. So yeah, these are some really nice expressions. Like instead sine x, exact same thing as x minus x cubed over 3 factorial plus x to the power of 5 factorial, yada yada, off into infinite. So yeah, it's pretty good. Power series. Now a power series is a sum of integer powers of x. So like if you had x plus x squared plus x cubed plus 5x to the power of 5 or something, the Taylor series is actually a type of power series. But it's nice. It's nice to know what a power series is because guess what? Convergence and divergence of a power series. You would never escape convergence and divergence. So, yeah, another thing. Okay. So this one's actually pretty specific. Like it doesn't have 6 million tests to memorize for a series convergence. What we have here for the power series, you have a power series. Power series always looks like this infinite series form because that's the definition of the power series. It will converge for all points in the open interval negative r plus a and r plus a. Or you can think of as a minus r, a plus r. That might help. Like it's just an interval going out from the a, and then r is the radius of that convergence, and then this interval itself is called the interval of convergence. So over this little interval here, your power series will converge for all the points in the interval, excluding the endpoints. So if your power series does that, that's what all this radius, all this interval of convergence pops out. How you prove this stuff? You take your ak and divide it by ak plus 1 and make k go to infinite. Now, I know this kind of looks like the ratio test, but this is the kth term over the k plus 1 term. Ratio test is the other way around. There's also an absolute value just slapped around everything here. So be a bit careful about this. Make k go to infinite, evaluate this, and this capital R, whatever it is, that's your radius of convergence. And it will converge absolutely whenever x is in that a minus r, a plus r, and it will diverge if x is outside that interval of convergence. If you can't find the limit, possibly it still does converge. It's another one of those theorems. So if you find R, congratulations, you can figure out all the convergent stuff. If you don't find R, potentially there are other things to worry about. And the endpoints, I have been hopefully trying to point out to you, this only works for within the interval, the a minus r, a plus r, but the open brackets here, you don't know what's happening at those endpoints. You'll actually have to sub in the endpoints to check out what's happening to that infinite series as it goes, whether it converges or diverges. Now, this is also reserved for 1, 2, 4, 1. So if you're in 1, 2, 3, 1, like that, ignore that last dot point. That's all you need for the top stuff. But also don't ignore the last dot point because don't you want the secrets of mathematics. So let's do a question with this one. It is actually pretty standard, no matter how weird these bullet points look. So you see this, it's a power series because it takes the form of a power series. Your coefficient here, your an, is of course the 1 over 3 to the power of m plus 1. Find the interval of convergence and then determine the behavior of the endpoints by subbing in. They don't say it by subbing in, but it is how you determine the behavior of the endpoints. So firstly, let's go through the common part, 1, 2, 3, 1 and 1, 2, 4, 1. You all share this beautiful stuff. we have, you remember, it's the nth term over the n plus 1th term, not the other way around. Don't do it the other way around. And see that little absolute value hanging around. It doesn't matter as much here because there's nothing negative, but it will matter in other scenarios. And then make n go to infinite. So what you can do here is you can try subbing in infinite immediately. You'll just have infinite on infinite. You're not going to be able to evaluate it. So what you need to do, divide everything by 3 to the power of n, then sub it infinite. Then you'll have 3 plus 0 over 1 plus 0, which is just 3. So you successfully found the limit r, and according to what we talked about before, that means your interval of convergence is a minus r and a plus r. The a here is, of course, it's actually also 3. You can see from the x minus 3 here, your a is 3. So your interval of convergence is 0, 6. You'll notice the open brackets because we haven't proved what happens at 0 and 6 potentially. They converge or they don't converge at 0 and 6. Or maybe they even converge for one and don't converge for the other. You don't know. Well, you do know because you can see the solution there, but I'm just spitballing out there, pretending you can't see the solution. So if you're 1, 2, 3, 1, this is pretty much where your journey ends, or it continues. But continuing with the rest of this question, to check out the endpoints, you will have to sub in the 0 and 6. So sub in the 0 and 6 into your actual original power series over here. So subbing in a 0 gives you this first infinite series, and subbing in the 6 gives you the second infinite series. Both of them don't pass the Cave test. Remember the Cave term test for divergence? If your AK doesn't go to 0 as k goes to infinite, then it diverges. So if you try subbing in, well, firstly, the first one doesn't even go anywhere. It doesn't approach anything because it bounces around between the negative and positive. And your second one, if you sub in that k going into infinite, it's just going to approach 1. Same technique as before. You divide everything by 3 to the power of n. And both of them fail the Cave term test divergence. So not fail, it pass it. So that means both of them diverge. That means your series doesn't converge at the endpoints since both infinite series diverge. So your interval convergence is still the open interval 0 to 6. If you proved any of them converge, like let's say you proved it converged at 0, you would actually have to change your interval of convergence there to just a closed bracket for 0 if it managed to converge at 0. And yeah, that's a pretty nice thing. Oh dear. Okay, observe the speed run. Manipulation of power series. You can multiply, you can add them, same deal as before. You can chuck out constants, you can integrate them, just do what you need to do to power series. A function that can be expressed as a power series, it will be differentiable and continuous as long as it's within the radius of convergence. So that's pretty powerful to work out the radius of convergence. The Taylor series. Oh, this question you can actually do really quickly. F of x equals sine of x squared. Write down its Taylor series. You know the Taylor series for sine x. Well, hopefully you've let that osmosis in from before. Sine x Taylor series is just this. If you've forgotten it, you can, of course, just evaluate it using the Taylor theorem formula. Sine of x squared, you swap out the x for an x squared, and you get the answer. You really do. Just swap out the x for an x squared. This interesting looking sigma form is just collapsing this whole thing down into a nicer general formula. And because the sine x always converges, since it converges for x's all real numbers, that means this series still always converges. So the radius of convergence is infinite because you cover all the values of x and it converges over all of them. So that's the answer for radius of convergence. Now, why we did the weird little collapse there of the infinite series, it would be really useful for part B when we determine an infinite series for the integral. In part A, we already worked out sine of x squared could be re-expressed as this interesting infinite series. So we go ahead, swap out the sine of x squared for the infinite series. So that's the application of part A. And then you just have to evaluate it like you would do an integral. Because this entire first bit over here, excluding the x, is just a constant. So you can just keep it, and then you can reverse power rule the x. So x is actually 4k, x to the power of 4k plus 2. So integrating it, you get x to the power of 4k plus 3 over 4k plus 3. And then you sub in the 1 and 0. 0 zeroes out everything. The 1, the x evaluates to 1. You're left with just negative 1 to the power of k over 4k plus 3, 2k plus 1 factorial. And you have it. You have the infinite series. So part B was really more of an integration question. You just had to get that initial substitution from part A when you evaluated the infinite series using Taylor theorem, which they also tell you to use Taylor series. And that's the end of the first section. Whoops. Any questions about that? Just pop that in while I go through applications of integration. We have a formula here. Just go ahead and memorize it. This is just a definition of what the average value of f is. So you have an interval a to b. The average value of f in the interval is just defined by this. 1 over b minus a times integral from a to b of f of x. Just go ahead. That's a definition. Memorize that. Beautiful mean value theorem. You already got one, like the usual mean value theorem. That's the second equation down here. This first one over here is just the version of it for integrals. So if you integrate from a to b of f of t, it will be equal to f of c times b minus a, where c is some mysterious number in the interval a to b. And once again, memorize that. Take it in. That's the mean value theorem for integrals. It's quite a lot of just a few theorems you really got to memorize. The arc length of a curve. So how long the curve is. There's actually several forms of this depending on how you get the curve. If they give it to you in parametric style, so if x and y are both in terms of this third variable, here it's t, it can be some other third variable. If x and y are both in terms of the third variable, you evaluate the arc length using this formula. You add the squares of the derivatives of x of t and y of t, square root that, and then go ahead and integrate it. It's important the path doesn't retrace. That is not so, it just means that your curve doesn't do a little loop-de-loop back. If your curve does a little loop-de-loop like that, you definitely got some issues there. But generally, you should be cool. They'll give you the curve and life will be great. You can go ahead and evaluate the length of the curve. Now, if it's more typical, if you just get y equals f of x, this is the formula you use for arc length. You just evaluate f dash x instead of needing to evaluate two derivatives here for x of t and y of t. So applying this in the 2015 paper, you have the cosine x. So this falls under they just give you y equals f of x. This is not a parametric. To evaluate the arc length from a to b, you go ahead and use the arc length formula. What this question also wants you to do is prove that this L you find, this capital L, is actually equal to the area, where the area is defined, it's just the area under the graph, between the graph and the x-axis. So that area, hopefully you remember the area is just defined by integration. The annoying bit is, of course, evaluating the arc length, but you do know what you're working towards because you're trying to prove it's equal to an area. So remember the arc length formula, you differentiate the f of x. So cosine differentiates to sine. So according to the arc length formula, that's square root 1 plus derivative squared, so that's sine squared x, and you have the bounds a to b. This 1 plus sine squared x is actually just cosine squared x, according to this identity, the Pythagorean identity. If you don't remember that identity, memorize it. Cosine squared x minus sine squared x is 1. Yes, go ahead and memorize that. Square root of cosine squared x is cosine x. Don't go any further than this because this question actually this is it. This is the evaluation. What you want you to prove is the question actually just wants you to prove that it's equal to a, and that is the literal definition of a. The area under the curve there is just integration of that curve from a to b. And that's exactly what you just proved for L. So that's where the question stops. It just wanted you to prove that arc length was equal to the area. You don't need to go further than that. And then applications and integration, just finishing up here, we have the arc length of a polar curve. That's the third form. They could try and give you a curve. If they give you r in terms of theta, so remember r's radius, theta is an angle. If they give you a funky polar coordinate, this is the formula you use for arc length. Square root of r squared plus the derivative of r with respect to theta, or squared. And then over some range of angles. So those are the three forms for arc length, just depending on what they give to you as the equation for the curve. Using that arc length, you can also work out some surface area formulae. If you have a curve and it's doing a little rotation around the x-axis, you can work out the surface area. There's three formulas here, but once again, they just depend on what the curve is. So the first one is the parametric, second one's Cartesian, third one's the polar thing. Depending on what they give you, you use the appropriate surface area formula. And a surface area formula is kind of, you can kind of try and intuition it. You can picture the curve rotating around. Yep, I cannot draw horizontal lines to save my life. You can draw that curve rotating around the x-axis, And as it rotates, of course, you get a circle out of it. So, to work out the surface area, you can picture if you work out the circumference and then multiply by the length of the curve. So like you have different circumferences along the curve, of course. If you sum all of that up, you'll get the surface area. And that's what the 2 pi y of t is here. Sorry, maybe it's more intuitive. 2 pi f of x, that's 2 pi, and then you can see the radius of your circle there. It's just the y equals f of x. So 2 pi r, there's a circumference, and then this is a direct copy of the arc length formulas. You can see the arc length formulas just in the back here, and then the front is just the 2 pi r thing. And the r changes, of course, depending on the equation of the curve via parametric, Cartesian, or polar. So go ahead, memorize those again. Surface area formula. There's technically only one version. It's just all polar, Cartesian, different forms. So we have a question here. You have a curve rotating around the y-axis. What its surface area? To be fair, they are trying to catch you out a bit since this formula is given to you rotating about the x-axis. You just have to swap out all the x's for y's and y's for x's. And you're good. Rotating around the y-axis is the exact same maneuver. So you can see this is a y equals f of x form. It's the Cartesian form. So you will be using the second version over here. Now this second version over here, it's for going around the x-axis. So you can just do a little readjustment here. Instead of f of x, you'll just be using f of y. And instead of the integrating with respect to x, you integrate with respect to y. Instead of a to b bounds for x, you have y bounds for a to b. So what that means, so here you have y equals f of x. If you rearrange this until x is the subject, then you will have successfully found x is f of y. And then instead of f dash x, you have f dash y. Now they give you the bounds as going from 2 to 3, but because we're swapping all the x's for y's, you use the y bounds from 0 to 5 over 4. You get the y bounds just by subbing in x is 2 and x is 3. You'll get y equals 0 and y equals 5 over 4 respectively. But then it's the exact same formula. So now the bounds describe the y instead of x. Instead of f of x, you have f of y. Instead of f dash x, you have f dash y. And instead of dx, you have dy. But everything is cool. Still the same formula essentially. And then it just becomes integration. So in the middle there, you just, not in the middle, in this square root, you evaluate that. Multiply these square roots together. Y plus 1s actually cancel. You have square root y plus 2. Chuck this 4 pi out. You know, 2 pi times 2, chuck it out at the front there. Evaluating square root y plus 2 is just a little reverse chain rule. You use up the y plus 2, and then it evaluates to y plus 2 to the power of 3 on 2 over 3 on 2. Sub in your upper and lower bounds, and you get the area. I do advise the putting on that unit squared, just to make sure you have the units for surface area. And I have sped run the lot integration. Sorry about that. That is the end of that. If you have the queries, then yes, I am here, I suppose. Is it legal for me to keep this running past 5? Yes, I am here. I am chilling. Yes. Yeah, you flatter me. Thank you. Yeah, I guess I'll just watch you trickle out, I suppose. Yes, we always aim to be. What do you mean? Math is always fun. I cannot believe. Yeah, okay. Yeah. Oh, you got the substitution thing, right? Yeah, it really is just a matter of usually they give it to you. And then if you don't, yeah, word of God, you just keep guessing it until it works. There's only so many they try out on you. Yeah, cool beans. Oh dear, no, come back. Well, there goes my stream. It doesn't look like there's questions. Looks like you're just casually, moving out into the great wide world. Good luck for your finals. Remember, math is the one true God. If you don't do a math major, consider it. Okay, that's all I needed to say. Goodbye. I'll go end this stream now. Yep. Shoot. I understand technology. Oh no.